Hello and welcome to experiment 8 of our radar system course. Today we will operate the full modular radar system. In the previous labs we have taken each component by itself. Now we will see how things are added up together to create the complete radar system. So it's quite fun experiment because you will see an actual radar application. Now we know that the first component in the transmitter side is the VCO, right? Because it's the model that is required to transmit or to generate the signal. We will use the same bandwidth and the same parameters that we have used in our previous experiment. So, how do I set my VCO? Remember, a peak to peak is 4. So I set the peak value to 2, right? And I have offset of 3. It's clear, right? Until now. Say everything is similar with the experiment 2 for the VCO. Now, VCO now is added to a splitter. This is the first time you see a splitter. What does it do? It splits the signal into 2 parts. Okay, the splitter is connected to the VCO to split the signal to 2 parts. One goes to the power amplifier, and the other one goes where? To the mixer. Okay, so the signal that is generated by the VCO, one goes to the power amplifier and the other one goes to the mixer because it will be our reference signal in our mixer. This operation is the same. Now the signal is in the power amplifier. It is going to be transmitted via the transmitter antenna. It will hit the target, reflects back, captured by the receive antenna. The receiver antenna passes it to the low noise amplifier. Are you with me until now? After the low noise amplifier, the signal is mixed with what? The signal from the transmitter, which we have obtained it from the splitter. When we mix these two signals, remember we have two frequencies. It's either the sum, which is a lot higher, or the difference. We don't need the sum, right? We don't need the high frequency. That's why we use low pass filter. So now it's like VCO, signal is divided. One is for the power amplifier to transmit. The other one is for the mixer. After it hits the target, the receiver gets it, pass it to the low noise amplifier, mix it with the original signal. The difference between them is the one that I want, but the summation gets filtered by the low pass filter. This difference, I will get what is known as the beat frequency. And we know that for stationary object, they are not moving. If I know the beat frequency, I can determine the range. And you have the formula in your manual, right? So simply, we will just do this for 3 or 4 ranges. Measure the beat frequency. You will see how it shifts by shifting the distance. And then from there we can find what? From the beat frequency we can find
experimental.
Yeah, experimental what? Range. Yeah. We know the range, but we want to see is it accurate or not. And of course there is some delays in the system. This delay will affect the measured frequency. That's why we have frequency offset. So we will calculate this frequency offset experimentally. So the operation is clear, right? Any question about the radar? This is very important experiment. This sums up everything we studied. Clear? No questions? No questions? Okay, remember just the basic things. 5 volt DC for the VCO to operate, 15 volt for the power amplifier, 12 volt for the low noise amplifier. And of course we have my tuning voltage. So let's turn on. By the way, there is another parameter that I have mentioned. TM, the period of my modulated signal. The frequency that I will give to my modulated triangle signal is 10 kilohertz. From there, you will calculate TM, okay? So FM is 10 kilohertz. Triangle signal, frequency, 10 kilohertz. Peak value 2, offset 3. Okay. from here, I don't know what is the range now, but just speaking in general, we can see that here, ignore this, we have this range here. This is my target. You will see that when I move this, it will start shifting. Look. What do we expect when I move it far? The frequency increase, right? So it should go that direction. Correct? Is it moving that direction? Do you see the logic? We will measure it, okay? But you got the logic, right? So I am moving far, my frequency is getting away. Because from the formula we can see that it's linearly, it is directly proportional, not inversely proportional. So what is the ranges that is written in your lab manual? Which one is the first one? 1.2. From 1.2, we know how to calculate the theoretical offset, right? The theoretical beat frequency. And now we will measure the experimental beat frequency and we will determine the offset. So what is 1.2? 2 squares, 1, 2, and like this. Okay. So we have 229.9. We can take it as 230 kilohertz. 230 kilohertz. Yeah, 230 kilohertz. Of course, we are expecting something small, not big, because we are subtracting, remember, my original transmitted signal with the reflected. So this is at 1.2 meter. The next one is 2.4, right? This is 2.4 meter. My beat frequency is 310 kilohertz. 310 kilohertz. Okay, you got it right? So at 2.4 it is 310 kilohertz. Next is 3 meter, right? Meter. We have 350 kilohertz. So at 3 meter we have 350 kilohertz. Last one, 4.2. It is 450 kilohertz. So at 4.2 it is 450 kilohertz. So now, and you have a table, right? You got your experimental measurement. You will find the theoretical ones from the calculations, and the difference between them gives you the offset. We are expecting similar offset because the offset is not changing. It's related to the delay of the system itself. For example, of my theory and the difference between theory and measurement in 2 meter is, for example, 50 kilohertz. it should also be the difference in 3 meter, in 4 meter, in 6. It does not matter because the offset is from the system. It's not changing. Cables, amplifier, antennas, they are not changing. They are steady. Okay, so you are, for example, if you get one offset 100 kilohertz, the other offset 500 kilohertz, there is something wrong. But differences of 10 kilohertz is not a big deal. Okay, so it's clear, right?
These experimental measures.
Of course, these are experimental, and you will do the calculations, and that is the theoretical measurements, and the difference between them gives you the offset.
Also, theoretical measurements.
You will do it by yourself by using the formula. Sorry?
FP.
Yeah, it's like the quiz. The quiz is this one actually. If you did this at home, you did the quiz.
Okay.
Okay. Now, what do you think when I move the target? This is just extra thing, not in the manual. No. Do you see? These are from the environment itself. Now there is no target. These was already there. Remember when the target was moving, but we had a beak that was moving with the target. Remember there was something around here, and then it started shifting and then shifting and then shifting. So now when we have no target, this is from the environment itself. Exactly. You can consider him as, let's for example, change the orientation. You see? Why? Because actually they don't see each other. For example, the transmitter is sending something from here, it's echoing from there, but the receiver is pointing that side. It's not receiving anything. But as they get to the same orientation, it sees the cluttering from the environment. Logic is clear, right? This is the real principal application of radar. This is the same logic. You can extend this from the lab to any real life scenario, airplanes, cars, anything. It's determined by this way. They measure the frequency, and from that frequency you can determine the range, the velocity, anything that according to your application. I think it's clear, right? This finishes the model of radar.